Hello, my name is David. This video is going to be about socks and about the German conductivity meter GMH3431 from Greisinger. The more salts and minerals that you have dissolved in water, the better it conducts electrical current and the higher the conductivity. It is not unreasonable to compare the GMH with the Russian AK-47, also known as the Kalashnikov. They are both highly reliable and rough pieces of equipment. Just as the Kalashnikov in many situations could be a soldier's best friend, for instance in combat, or perhaps as diamonds are some girl's best friend in other situations. The GMH could be very instrumental to any scientist who wishes to investigate water and properties of water. The GMH comprises a probe in which you'll find stainless steel electrodes between which the conductivity is measured. It also comprises an internal temperature sensor. The GMH also comprises 6 push buttons with which you can change the settings of the instrument and a display on which you can see the data. If we move over to the GMH instructions manual, you'll find that it could measure a lot of things which are dependent on the conductivity. But today we are going to focus on the conductivity in microsiemens per centimeter in itself and also on the TDS. TDS stands for totally dissolved solids and is related to the conductivity. By applying a factor to the conductivity, you could get an estimate of the totally dissolved solids within that water. So let's find out if the GMH is an accurate instrument or not. For that purpose, we'll need a reference solution. In this case, we have a reference solution with a set conductivity of 1413 microsiemens per centimeter at 25 degrees Celsius. So what we will do here is to look at the conductivity, or rather the conductivity which the GMH tells us at different temperatures. And we're going to let the GMH report the measured conductivity with no temperature compensation, with an internal non-linear compensation as well as an internal linear compensation to see how these values compare. In order to do that, we'll begin by heating the entire container with the reference solution in a microwave oven for about 30 seconds, after which it will have attained temperature of roughly 60 degrees Celsius. And then we'll just start up the instrument and dip the sensor in the solution and let it stabilize. We could get a first reading at 2170 microsiemens at 52.5 degrees Celsius. Let's feed that into the table. Then we'll set the GMH to apply a linear compensation. And after a while, after having allowed it to stabilize a little, we'll get a second reading of 1396 microsiemens at 50.3 degrees Celsius. We've got a second data point to feed into the table. Then we'll just repeat this over and over. As the solution is dropping in temperature while sitting there and cooling off, we'll reset the GMH to measure the conductivity either without any temperature compensation or with a linear or non-linear compensating algorithm. And when the temperature has dropped down to about room temperature, we're done and we could take a look at our data. As you can see, we now have conductivity data of this reference solution all the way from about 50 degrees Celsius to about room temperature. Let's plot the data. And let's remember that the conductivity of this particular solution is 1413 microsiemens per centimeter at 25 degrees Celsius. So we expect the instrument to somehow come to the same conclusion. When looking at the conductivity without any temperature compensation, we'll see that it has got a roughly linear relationship with rising temperature. Thus, the higher the temperature, the higher the conductivity. And we might also note that both the linear compensation mode and the nonlinear compensation mode does a pretty good job. All curves cross through the expected spot, and it indicates that the measured solution is 1413 microsiemens at 25 degrees Celsius, which we know that it is. Thus, the accuracy of the instrument passes the test. Not only did we measure the conductivity, we also measured the TDS, totally dissolved solids. When plotting the TDS values, we might note that there is a little drop as the temperature rises, but we could still conclude that the instrument gives us an estimate of a TDS value of about 1400 mg per liter. Let's look at tap water in the city of Lund in Sweden. We'll just repeat the whole sequence again. Heat the water in a microwave oven to about 60 degrees. Let the instrument measure the conductivity and the TDS as the temperature drops naturally. After a while, we'll have our data. Also here, we'll see that without any temperature compensation, the conductivity is increasing as pretty linearly as the temperature is increasing. The linear compensation mode is pretty good here as it sets the line more or less horizontal, while the nonlinear compensation results in a small underestimation. Anyhow, these lines cross at the same place at 25 degrees Celsius, and from that we could get a good estimate of the conductivity of tap water in the city of Lund. And again, of course, we measured the TDS. From the plot, we could come with an estimation that tap water in Lund contains about 200 milligrams of totally dissolved solids per liter. This is molecule water, and it's the golden standard pure water that you'll find in a decent lab. You might call it ultrapure water. Same procedure as all times before. Let's heat the water in the microwave oven and then do conductivity measurements as the temperature drops. With this highly pure water, you might note that the non-linear compensation is better than the linear compensation. And now over to the TDS. We could conclude that this water, according to the instrument, has about 1 milligram of dissolved solids per liter. A pretty pure water. Other ways to put it is that this water is 1 ppm in dissolved solids, or that this water is 99.9999% pure. So far so good. The GMH is working well. So now what? What shall we do with this powerful, rough, and highly reliable and accurate instrument? Well, you could of course always measure the conductivity of some free coffee that you might find here or there. And maybe you could compare different coffees at different places. Even though that is fun, we could do better things. We could actually initiate a real scientific study. We could study the sock mineral extraction with molecule or ultra-pure water to see how the sock minerals are extracted and transferred to the water. Let's start off with molecule water, which is highly pure, having a TDS of about 1.1 mg per liter at about just roughly 30 degrees Celsius. Then we need a sock with some sock minerals originating from human sweat. And let's soak that sock in this ultrapure water to see if these sock minerals are transferred to the same. So we could conclude that in this first extracted procedure, the sock turned the previously pure water having a mineral content of about 1.1 to a water with a mineral content of about 425 mg per liter. Seemingly, there has been a lot of minerals transferred from the sock to the water. Let's do it all over again. Surely most of the minerals must have been removed from the sock at this point, and we'll squeeze out as much water as we can, and we'll provide some new fresh ultra pure water and dip the once washed sock in that water to see what happens. And what do you know? See and behold, the mineral content the second time did not reach 425. It reached only about 107. As expected, most of the minerals were removed from the sock, and there were not as much minerals to extract by the water this second time after the first wash. Just as expected. Let's repeat this a few more times and see what we'll end up with. After having extracted the sock 4 times and pressing out as much water as you could do by hand in between each time, we'll end up with a final mineral concentration of about 28 mg per liter. The first time we dipped the sock in ultra-pure water, the mineral content of the water rose up to 425 from about 1 mg per liter. After having washed the sock 4 times and then finally dipping it into ultra-pure water, the water rose from 1 to 28. Now let's take a look at the details. After having washed the sock the first time, when you dip the sock in new fresh water, the mineral content decreased about 4 times as compared to not having washed the sock at all. While after the second time, the mineral content only decreased 2 times. And after the third and the fourth wash, the mineral content did not decrease much at all, actually less than 1 time. It seems like the amount of minerals which are given off by the sock decreases rapidly after the first few times of extraction, while after that the mineral content which is given off decreases hardly at all. Look at the red arrow, which is flattening out much more as compared to the green arrow in the beginning. When you think about it, this is not what is expected at all. You expect a constant dilution factor, and what we do observe is a decreasing dilution factor. From the first wash, the dilution factor was 4, and in the second, the dilution factor was about 2. And then it decreased even further to be less than 1. Why is that? So, could this decreasing dilution factor be explained by relatively hard-bound minerals on that sock? Minerals which are slow and difficult to release, but still release steadily into the surrounding solution. Or could the decreasing dilution factor be explained by the release of tiny fibers from the sock itself? For instance, could it be that the cellulose of the material is giving off small pieces of polymer which releases itself into the solution. Such fibers must have an ability to carry an electric charge through the solution as they actually give rise to an increase in the conductivity. Well, let's forget about the mechanism right now. Let's look at the results. When dipping the sock the first time in this ultra-pure water, the water became mineralized to a level which actually exceeds the tap water of Indianapolis, which is a really hard water. After having washed the sock one time and then dipping it into new fresh water, we reached a level which was somewhere in between the tap water of the city of Lund and the city of Memphis, which has a pretty soft water. Washing the sock further gave a water which was just a little shy of the common tap water in Memphis, which is about 45 mg per liter. Thus, a sock which has been washed 4 times in ultra-pure water to turn ultra-pure water into the tap water of Memphis, roughly. But, as it very often is with science, we are left with more questions now than when we started off. For instance, what kind of mysterious particles are released from socks? Particles yet unknown to mankind. How do these particles affect the water they are released into? And could these particles be dangerous? Only science could tell. Further experiments are clearly warranted.